It's obvious. CUDA for GPU, CUDA, then CuPy, Numba, and then OpenACC. Right. So, these are things we covered in the class, and okay. So, now we are going to multi-core. Okay. Most people use multi-core even now. GPU is a new tool. Okay. So, it has not become very popular. Still many codes in IIT or abroad as well, people use multi-core. Multi-core means more cores, not GPU. So, we should also know how to program multi-core. Okay. So, I am going to go to that. We did one piece before, well, two pieces before. What are, well, three pieces before, sorry, I should say three. What all did you did for multi-core? Anyone? Excellent. Multi-threading with Python, okay? Multi-processing, proc and Numba, okay? So, Numba converted to C code. We didn't need to worry about what was there inside, but Numba is a very good tool. It gives a very good performance. So, the code which is expensive computationally, you can just say Numba, okay, whatever the syntax. So, it is like compiler command, the way we did for OpenACC. Similarly, Numba is acting like that. Okay. Numba says, well, this part I need to, the programmer wants me to convert that to C code, compiled C code. So, these were working for, this would work for multi-core, and this is for Python platform. Okay. Oh, yeah, MPI4Py. Thank you very much. I die for MPI4Py. MPI4Py also we can use to use multi-core. So, there are these tools. Now, so what I am going to do now, I am going to go to C language and show you tools which can be used for multi-core. Okay. OpenMP is one such, is quite simple, is very similar to OpenACC. Okay. It turns out OpenMP can also be used for GPU, but I will not get into that. Okay. Once you know OpenACC, OpenMP is similar performance. Okay. So, one more thing I would say that these tools are not repetitive. So, everyone has some unique feature. They may be, some tools are less time intensive, like CuPy, you don't need to spend too much time, but it is not as fast. Okay. CUDA is super fast, but it takes time. You need to worry about threads, all that. Okay. Anyway, so let us get to OpenMP. So, OpenMP is for shared memory architecture. That means, memory is shared across all the cores. So, it will work for single node. Okay. It will for single node with many cores. We have one memory and we have many CPUs, many cores. By the way, this cores could be single CPU or more CPUs. OpenMP works for multi CPU as well, but as long as they share memory. Okay. So, all these guys will use this memory. Okay. So, let us see, if you are expert of OpenACC, OpenMP is piece of cake. Okay. It is just very straightforward. So, it is the library for shared memory within a node. So, it also works for Fortran. Okay. So, Fortran has OpenMP support, but I will cover C only, not C++ also. C++ and C are very similar. So, let us stick to C. So, parallel is the expensive part of the loop using threads, the ones which are time intensive. right. So, you have still have the sequential code. We have sequential code and we want to just use many cores without changing it to parallel, like parallel will be try MPI, okay, which I will do it after this presentation. Okay. So, we have sequential code, we just parallelize expensive parts using threads. So, use compiler directive. Okay. So, the programmer is telling the compiler that this part has you do something on this part when you compile it. By the way, these codes are not, they do not have object code for corresponding to this compiler directives. Okay. So, x equal to 5, y equal to x square, all these have object code, no, zeros, ones inside, and they are executed one by one. But if you look for inside the object code, you will not have anything corresponding to this. This is instruction to the compiler, right. You understand, compiler is one which is converting your C code to object codes. So, this is telling the compiler, okay, I want you to do this, and now compilers are smart and they can do this stuff. So, compiler generates parallel code for threads. Threads are generated for the task and destroyed. This is important. Okay. Threads are, once they are done, they exist no more. So, you can think of your main program, sequential program is following a thread, one thread, main thread. Then at some point when pragma comes, it generates several threads and they do work in parallel. It could be, for example, summing up arrays or A star B sum, matrix multiplication. So, they are expensive for large matrix. So, once you are done, then they join and we only get one thread after that. So, this thread continues. Quick way to achieve parallelization. This again one day's work for a moderately large code. If you have 5000 lines of code, then you can spend 2 days to make it parallel with OpenMP. MPI will take time. Okay, MPI may take a month or so. Okay. However, with limited gain in efficiency, because you are only parallelizing some parts of it, but it turns out OpenMP can give you good gain. I did test on my laptop. Okay. So, I hope this Suman is saying that he will test it on a multi-core machine. Laptop has a problem that it has other processes running. So, it is not the, you will not get a very good, there will be some loss because of my mail is running or web browser is running. So, it is good to run on a machine which is dedicated for parallel processing. Okay. I hope that part is clear, because they should not be running other things. By the way, our computer center HPC system, those compute nodes, so the compute nodes, you understand, no? There are nodes which are only computing. They do not have web browser, they do not have email, nothing, they just compute. Okay. They may have Python in each compute node, but they just run the jobs, means compute jobs, what programmers are firing. Memory and cache management. So, this is the issue with OpenMP. We discussed it while discussing multi-threading. Okay. This issue will come here again. So, okay, I must say multi-threading of Python is equivalent to what I am telling now. Okay. So, what you learned for multi-threading is just translated here, nothing different. So, we remember you had race condition. What is race condition? Which I will come to it in very soon. One variable is, so many threads are approaching one variable for updating, and then there will be problem, no, if two guys try to run after same variable, it will be a problem. False sharing, we discussed, is very tricky issue, but false sharing was when we are doing a matrix Ax equal to y. Okay, false sharing was an issue, and thread safety. Okay. So, this part I will ignore, but this one, these two we have discussed. Here I will focus only on race condition. False sharing, well, we discussed it, only the syntax is changing, the ideas are not changing at all. So, we have the sequential code. So, I want to make part of it parallel. So, then we use this pragma OMP parallel. You just need to say this before that code, and if you are using, well, there are several ways to give pragmas, but this is one simplest possible way, and once you do it, then you should enclose the code which is made parallel within braces, and C uses these braces. Okay, these braces. Okay, this tells you that this part of the code needs to be parallelized using threads. So, the code is there in the next slide, but you need to put braces. These braces are important. It turns out sometimes braces are required, sometimes braces are not required. Okay, I am going to show you one case where braces are not required. I had put some braces and it was not giving the correct result. So, sometimes there are one more point. Okay. So, how many types of errors are there in computing, and which is the most difficult to solve? Okay, so that comes under a different class. So, there are three types of errors. Let me just make this clear. One is compilation error or syntax, is connected to syntax. Okay. So, during the compilation only it will tell you there is a problem, and this part is easy to debug. In fact, compiler tells you few things. This part, the braces are missing, bracket is missing, variable not declared. So compiler is also helping you, and if you are reasonably good in programming, you can easily debug this. Next one is runtime error. Okay, but for example, segmentation fault. Okay. Segmentation fault is difficult, is annoying, but it is it's annoying, but is manageable because you can put various debuggers pointers, or you can, well, I use printf. Okay, just print keep printing. Where is it? Where is the segmentation fault occurring? You can get there. Okay. So, this is a runtime error, and third error is logical error, where your program is running, it is giving output, but we do not know the result is not correct, or sometimes you do not know the result is correct or not. Okay, you get a number, but how do you know the result is correct? Okay. For some of the projects, we have some constraint that with viscosity 0, Navier-Stokes equation should conserve energy. Integral of u squared by 2 dx must be constant. So, this is the condition we need to put, because the code is running, we do not know code is correct or not, how do I test? So, these logical errors are very hard to figure out, this is the hardest, because it is giving you result, I do not know where the problem is, and again you have to suppose printf. Okay. And sometimes one test will pass, but the next test will not pass. So, this is the thing. So, the braces sometimes it does not give error, but it gives you something which is not correct. So, you need to worry about these braces actually. OpenMP, that was the issue which I faced. Okay. So, this is the code for hello world. Okay. So, I will also tell you how to run it. So, both are required. Okay. So, side by side. So, I am going to run. So, this is the same C code, sequential C code, but it has some OpenMP sitting there. Okay. So, first one thing is these are standard, right, stdio, stdlib, but we have OMP, and I hope everybody knows about stdio and stdlib. So, there are standard libraries, std for standard libraries, they have printing, some standard functions like sin, cos and so on. So, OMP is a our OpenMP, and header files are sitting in omp.h. Now, this is the main program. It was sequential code, but I am adding few things. Sequential code would have been just this: print greetings from hello world. Okay, this is like hello world. What we say, well, how many threads I am using? So, I say I am using 4 threads. So, int thread count is 4. So, I first need to give how many threads I am using. Then pragma OMP parallel. So, this is parallel. Okay. So, it is going to tell you that whatever is there inside should be parallelized. And what is inside? Int id OMP get thread count. So, what does it tell you? Thread sorry, not thread count, thread number, okay, count is different, thread number. So, what does it tell you? Every thread has an ID, okay, every thread has a unique ID, has a unique ID, like MPI also had unique ID, thread ID. So, we saw that in Python, okay. So, every thread has an ID, and how do I get the thread ID is by this function OMP get thread num, this part of OMP library, okay. So, ID is there. Now, then I say print greeting from thread and ID. So, this is the type format and braces close and return 0 means the main program is ending now, and that is it. So, what is that going to give us? Exactly 4 times this greeting from thread, but thread ID. So, every thread will print its ID, there will be unique ID, and IDs will range from what to what? 0, 1, 2, 3. Okay, so, 0 to 3. So, this is output. Okay, so, this greeting is from some other program. So, hello world from thread 1. So, instead, so this would have been greeting from, okay, thread 1, thread 3, thread 2, thread 0. They are not coming in sequence like 0, 1, 2, 3, but whichever thread finishes prints gets access to the monitor, it will print it. We saw that before. Yes.
In this program, we are not passing the thread count in the OpenMP get thread.
Yes. So, here I am defining the thread inside the code itself. In the next program, I am going to show you how to get from the here. From the command line. Okay. It is true, I hard coded it, which is, so he is saying that why, I mean this 4 is bad, no, because if I want to use more different threads, the number of threads, then I need to recompile the code.
Thread count is kind of convention, or like we have to pass that number in the ID, right?
Not necessary, this works. So, you can put inside as well if you like, no problem, this will work. So, the next code is what you are after, I believe. Okay. So, this is the code which I had just now, but I am going to change it. So, that my number of threads I pick from the command line. So, I would basically want a dot out and number of threads, it could be 4, it could be 10, whatever number. So, in the last class I showed you how to use argc and argv. Okay. So, you can use that argc and argv, it is going to pick up the command line, okay, and from command line it is going to figure out how many threads you want. Okay. So, this is argc and argv, we did that in the last class, and thread count. So, here thread count is coming, okay, it is a variable. String to long, remember we did that in the last class, string to long argv1. So, what is argv1 in this line is a string. So, this is argv0 and this is argv1. So, it takes argv1 which is a string, it is a string. So, it has to convert to integer, but integer what base? 10, base 10. So, this base 10, okay. So, it is converting it there. So, I get thread count, and after that I this code is same as before, this code is exactly same, okay, and it will print that greeting from thread 0, thread 1, all that. Any doubt? Okay, clear? So, this is how we get this one. So, this is what I wrote, a dot out. So, a dot out we can give the number of threads, but while compiling, please, I forgot to tell you that you have to give this option minus f openmp. This was there in the previous slide, this one, this option. Without that, it will not use openmp. It will say, well, which, I mean, it will assume normal C code otherwise. Okay, so that's thing. Okay, now let us do the real example, sum A star B. This we have been doing it for all sorts of parallel programming. So, this is as before, we have two arrays A and B, which are integer arrays, no, actually float arrays, they are float arrays here, and I multiply and element by element and sum. So, the standard thing was I just sum, no. So, this is sum A I B I. So, when n is large, it could be billion numbers, then I can use threads. So, by the way, if the number of cores on your machine in a node is 32, then how many threads should you use? Sorry? 32 only, okay, shouldn't use 64, though it may say, well, you can use 2 threads per core, do not use, see, each core 1 thread, okay. 2 thread does not give better performance so far, okay, that is what we have at present. Maybe the new cores may have that facility, but not yet. So, problem is again, so we will have a total variable. Now, total is going to be updated by each thread. Let us go through the code actually, I would like to say n is large number, which whether this is part of the code or not the full code. So, n will be declared sometime before. So, n is a large number and I am putting inside this OMP parallel, this you have seen it before, but as a for is a for loop and number of threads, thread count. So, all that would have been obtained before. So, thread count is coming from arg V1 and all that. Okay. Now, what is it telling you that this is a for loop, that part you make it parallel by how many threads, thread count. So, you are not going to decide that it should be divided equally or what, you do not do anything. Let the compiler decide, let the computer decide in fact. Compiler would have written a code, so that for any number of threads, it will divide equally, but it is not your worry. Okay. So, for billion n will be billion, so n is let us say 10 threads, then is billion by 10, 100 million. Is that clear? So, you do not divide yourself, that is something you should never do. And but each of them will have, so there is a total variable which is going to be updated by these variables, by these threads. Now, there is only one thread, then no problem, this total will be updated one by one. Whether each thread will work in sequence, is that clear? So, imagine we have 16, n is 16 and number of threads is 4. So, there are 16 numbers, 16 AI and 16 BIs, I can't okay like that. Okay. Now, you multiply them, so you get a number and total will be updated. But the 4 thread, so 4 guys will try to update this total simultaneously sometimes, or at least 2 of them may be, it may happen that 2 guys approach total simultaneously. Then what should we do? So, you should avoid this race condition, this is a race condition. You should tell that okay, one at a time, no 2 are allowed. So, we can do that by putting critical, pragma OMP critical, and then total plus equal to AIBI, okay, multiplication and addition. But okay, so this is make sure, this will make sure that two threads do not come simultaneously to update total, or more threads, two or more threads do not come, and this has to be within braces. That is another condition, it has to be within braces. Okay. So, total is updated by each thread, and this is to avoid race condition. So, this critical is a very important keyword. Here I is a local variable. So, just few things that I is a local variable, and computer will divide the loop equally among threads. Okay. So, this is just straightforward, but yeah, we learnt few more things, that we have this for loop, and how to use for, parallel for is here. So, there are several. So, race condition is important concept. So, I showed you how to avoid it by using critical. Okay. So, critical segment assures that two guys do not come simultaneously. Now, there is another way to avoid this is by atomic. Okay, we have done this before for Python. You can also do it for OpenACC. OpenACC has very similar structure, you might notice, but OpenACC codes can run on GPU as well as on CPU. I did not tell you how to run on CPU, okay, but you can just look at Google. OpenACC codes will run on I think I did tell you, I am not sure. I believe I told. So, OpenACC can, those codes OpenACC, they can run on both multi-core and GPU, but this option does not exist with NVCC. NVCC we can run on GPU, but not on multi-core. Okay. But there is a compiler by Portland Group PG. I am not sure, some of you might use this Portland Group compiler. Now, Portland Group compilers have been bought by NVIDIA, okay, but Portland Group compilers gives you the option, so you can use it in multi-core as well as in GPU. So, Colab you can't use on multi-core, the OpenACC codes, only GPU, but PG compilers can. Okay. So, atomic is also a part for using avoiding race condition. So, what do we did? What should be done here? We just use pragma OMP atomic, not critical. That is atomic, and this is same code, except I change critical to atomic. But there is one more change. The braces are gone. No, there were braces before. Here and here for critical, braces are not there. So, for atomic you do not have braces. If you put braces, you do not. It does not give the result, correct result. Okay, that is where I was struggling. So, load and okay. Now, there is one more point. So, which is better, atomic or critical? So, there is a subtle issue. Atomic is better. So, what does atomic do? So, this load and store operation. So, what is loaded? The total is loaded inside the arithmetic logic unit. The one of the register will get total, then AIBI will be computed. So, everybody knows, no? Now, this part of the hardware you should know, that every CPU has a ALU which does the computing, then their cache and registers. So, whatever number multiplication or all the operations happen inside the CPU with the help of ALU. ALU is a calculator, and is going to take data from where? From the registers. So, register will get total. Well, in fact, total will remain permanently. Okay, total is not going to be brought back and forth. Okay, but there is only why is it that? For locality, every time you, so this is called temporal locality, no, we discussed that before. If you bring push back in main memory, bring it back is expensive. So, the compiler definitely knows that total is used very often. So, I will keep it in the register, it is in the cache. Okay. So, total will be in the L1 cache for sure. Okay. So, from L1 cache it will come to register, it will load, that is loading, update this, increment it, not increment, it means update by AIBI and put it back in cache. So, load and store operation should be atomic. What does it mean? This should be done by a single thread at a time. You understand, two people cannot try to, two students should not go to the register simultaneously, one at a time. So, load and restore is atomic, but multiplication, this evaluation, this one can be done in parallel. Because atomic ensures that each guy can, you keep computing, you keep it in your temporary location wherever, but updation will be done by atomic operation. Okay. So, that is advantage with atomic. Critical does not bother, critical says, well, you go here, multiply and add, but that time nobody else will come. So, no interruption allowed between load and store operations, and no brushes. Okay, this is something we should keep in mind. Now, what kind of operations are allowed? So, here this is called binary operation. No? So, by the total, everybody knows plus equal to, what does plus equal to means? This means total equal to total plus AIBI. Okay. So, this is binary operation, it takes two operands. So, we can write in this way, and so how many binary operations are allowed? Plus, star, division also allowed, and there are some more like logical operations and, or. So, quite a few are allowed. Also increment operators. So, these are uni operators. So, x is there and it increments. So, these are also allowed by atomic thing, and the uni operators. Reduction clause, this is the third way to avoid a race condition. So, this again we have done it before. So, the for loop, by the way, this is should be in one line. So, pragma OMP parallel for num threads, thread count, reduction plus, but which variable? Total. Okay. So, this is a variable plus colon total. Okay. Now, there is no change in the loop. Inside the loop we are doing nothing except, well, only thing we made a change is this, the reduction operator has come. Okay. So, it tells the compiler that this plus operation is atomic operation. Okay. So, it should be done by one thread at a time, and there are more operators which allow this. So, plus, minus, star, ampersand, this and, or, what is this one? Not, this logical and, logical or, and each thread makes local. Okay. So, one more important point, reduction clause is, so here each variable, each thread will make local copies of total. So, it is like some local sum, no, we had variable local sum, and then it will be finally make the total, final total. Is that clear to everyone? So, the three ways to avoid race condition. So, you can choose whatever you like, but use either atomic or reduction. So, variable scope. So, there are three types of variable in OpenMP: private. So, these variables are local to a thread. That means, let us say thread 0 has variable I, then thread 1 also would have variable I, but these i's are separate. Please recall that every thread have their own. So, there is global memory, but there are local stacks, right. So, there is a word stack. So, each guy may have different i's, like for loop I know. So, the I could be local, but some variables like total is shared. So, so this is private, shared, which is shared among all threads, okay, and the reduction variable, this is separate type, which is everybody will make a copy, perform reduction on the variable that appears with a specific operator. So, they make their copies and then update it, okay, like local sum each of them, and then all the local sums are added. But you see, you do not have to do it yourself. In MPI, what do I do? So, every processor makes local imp sum, then thread 0 master thread will take all of them. Okay. So, it is more lines of codes. MP with OpenMP you do not need to do that. Okay. So, there is one more important point, is recommended when you use OpenMP that you declare all the variables. In the sense, if it is to be shared, then it should be declared shared. If it is private, then it should be declared private. Okay. And so, it is just that compiler knows and you do not make error, programmer does not make an error. So, recommended to use default, and this should be just above the for loop. Okay. So, essentially we provide parallel for loops, and also one more point, for parallel programming do not put if condition inside a loop, do not use while loop, until repeat until is also not a good way. They will have condition, no. While also has condition, no. Each time it will check, who will check. So, that is the parallel programming is, these are to be avoided, do not do that. So, this is the line, which is a long line, but suppose, well, if it is too long a line, then you can't fit in one line. If it is too long, then you can't fit in one line, then what do I do? I can use this backslash to line break, okay. But if you do not put this backslash, it will get an error. So, we need to put this backslash if you want to use multiple lines, okay, for pragmas. So, let us look at some example. This is for y equal to Ax, this we done it before, matrix multiplied vector. So, I have this I j variable, this I j variable must be outside. So, there is one more point, if you do it inside, that anyway is, so it should be outside if you want to make it private. This is another error I was making. So, it should be declared outside. So, now it is private I j, default none, and shared is, what are the shared variables? E, x and y. But there is one more advantage, shared means they will not be copied. Each thread should not make copies of this big arrays. So, shared arrays. So, this I loop is there, j loop is there, and I am just updating it, and this I j is already declared. So, no problem, and they are private. Will there be a race condition here? Because remember this matrix A, this matrix A, and you Ax. So, this guy will multiply, no. So, you will divide the array A. So, the compiler is smart, he is going to divide like this. If there are 4 threads, then they divide the rows of array matrix A, and then each thread will be doing independently. Is it clear? So, this will be basically y is for thread 0, this will be y is for thread 1, y for thread 2, y for thread 3. So, there is no race condition in this. So, matrix multiplication pretty similar. So, I have this int I j k. So, this is done inside a function. You can also invoke OpenMP within a function. This is matrix matrix multiplication, A, B, C arrays and M and P. These are the 3 sizes along x, along y, along z. Well, sorry, not 3 sizes. Yeah. So, no, 3 sizes are not that. this is m comma n, second is n comma p, and third is m comma p. Okay. So, this is not 3D, but it is this. Okay. So, I am going to use pragma om p. So, there are 3 loops, right, the 3 loops here. So, I just do it before for loop, and before that I have this another declaration pragma OMP here parallel, there is no for here, okay, but it is declaring the variables shared and private. So, the variable declarations are done first, then this part is that pragma scope, and next pragma scope is this here. Well, I think I am missing up a bracket. This bracket corresponds to this, and this bracket corresponds to this. Okay. So, so the for pragma is controlling this part of the code. Okay. Now, the schedule static, I do not want to get too much into it. It is basically telling that you do it statically. So, there is not done dynamically, the other one is dynamic. So, it will be changing with the run time, but I think you do not worry, I just took the code. So, I have written it here, they are done mapped statically at the in a round robin RAM. So, it is static allocation, it is not changing with time. So, when the code comes here, it will decide how many, how do I separate, how do I partition that array, okay, and it is being done here. Again, I do not need a race condition, avoid race condition by atomic or something, it is done there. Okay. And this trick you already know that I am basically using 1D array rather than 2D arrays. Okay. So, where does OMP fail? OMP does not work everywhere. Okay. So, if there is no clear division of task, like if you put if statement and so on, it is not going to work. Even while loop, no. Also, Fibonacci sequence, this is a recursive function, right. You can, Fibonacci sequence can be generated both recursively as well as iteratively. Okay. But if you define it recursively, then OpenMP will not work. Okay. So, recursive will call the function again and it is not going to work. Gauss Seidel is another thing which I have not done it. So, I can't tell you, but this does not have clear loops. We want clear loops, that is important thing. Now, let me just tell you some timings. We did this for Python, but I did it in my laptop for OpenMP as well. So, the OpenMP without optimization, and this with optimization. Okay. So, with 1 thread, 2 threads and 4 threads, you can see that there is a improvement, right. From 1 it came to 0.54, which is halved, and 0.54 to 0.299, which is around 0.3. So, efficiency was time taken multiplied by T serial divided by T parallel multiplied by number of threads. So, with 2 threads it is 0.99 and with 4 threads it is 0.89. It is great, this is very good. With optimization it does much better, okay. The numbers are down by huge factor, okay, more than a factor 10. But this is for this Ax equal to y. Okay. So, this is when we are dividing when A is 8000 by 8000, okay, is very good, but when it is 8 by 8 million, then without optimization numbers are 1.16, 1.15 and 1.10, practically no advantage of threading. Why is that?
Because there are more number of matrix in the y direction
Okay.
in each thread, so they have put one.
So, that was false shading. So, this was a difficult concept, but in cache this part was coming. So, this was when you update this guy is confused. So, you have to look at the discussion on false sharing. So, so something called thread safety or thread concurrence. What is thread concurrence? So, every variable has their copies in your cache as well as in the main memory. If they do not, if they are not in sync, computer is confused. Okay. You understand? I mean, if your electronic what you are is there in your bank, and if your if your passbook or your in your computer you do not get the same number, it is a problem, no. So, similar. So, this is the issue, false sharing. Okay. So, it turns out for this case, when I update this and this is shared in that cache line. So, cache line has length 80 thing. So, it is shared in cache line, and that has a conflict with the main memory. So, false sharing is certainly tricky, and all the OpenMP or shared memory stuff suffer from false sharing. Interestingly, GPU do not have this issue of false sharing, neither cache mesh. GPUs are, the data comes in huge numbers, okay, and they operate on the data like that army unit, you know, they just do one by one, tuck, tuck, tuck. Okay. So, this is the issue, but interestingly, when I employed minus O3, then it disappeared. So, you can see the efficiency with minus O3, the number is 0.09, 0.04, 0.02. So, it did something inside, okay, with O3, which I do not understand. So, this is a multiprocessing, multithreading numbers, this with Python. So, you can look at the number, just focus on this number 0.528 multiprocessing, and this number is 1.07. So, is factor, okay, wait a minute, this is well, roughly same order, but yeah, for this case, when I compare with minus O3 option. So, with multi-core, of course, I am going to use minus O3 option. I am not going to compare the number with without option. If you look at the number here, it is 0.08 with minus O3 option, but with single processor, Python is slow, is 0.332. Okay, at least on my laptop it was slow. So, for Python you should use just vectorize, okay, that is what you should use, that gives a good performance, or use Numba. Vectorize will be similar, because vectorization is using C code in the background. And so, if you compare it with minus O3 option of C, Python is slower without any vectorization, which is multithreading, it is slower. So, multithreading, if you are using it, okay, anyway. So, we have to use OpenMP. Okay. So, summary, OpenMP without optimization, no speed up for 8 by 8 million, but all cases speed up with minus O3 optimization. I do not know the answer yet. C++ is around 10 times faster than Python, blank here, multithreading and multiprocessing. So, Numba is way to probably speed up.